One.
Yeah. All right. So we're going to do Kirchhoff's current law for this middle node. So we've got VL over, no, we've got I, because that's the current leaving that node, plus VL minus V over 6 is equal to 0. Yeah, this will work. Okay? That's Kirchhoff's current law right there at that middle node, which is that, and so that's the last step in the node voltage analysis, because I just did Kirchhoff's current law at the two non-reference nodes. So this was my first equation, and now my second equation is here, but I got to work at it a little bit because I don't like this term, because it's not one of my state variables. You want to make sure that you end up with an equation in just the state variables, and my state variables are V and I. There's no VL, so I've got to change VL. And I can do that pretty easy because I know that the relationship of the voltage across an inductor to the current, remember what that looks like? The relationship between the current through an inductor and the voltage across it is what? V equals L di dt. That's the relationship. So in this case, VL, let me multiply everything by 6 just to get rid of my fraction. So I've got 6I plus VL minus V equals 0, and I want to replace VL with L di dt. And there's my second equation in my two state variables. So now I've only got the state variables in the equation, V and I. Great. So I'm going to erase everything except those two equations in the two unknowns, because that was the whole purpose of this first part of the solution, where I'm looking for the differential equation. To get the differential equation, the first step is to find n equations in the n unknown state variables. So in this case, it's two equations in the two unknown state variables, V and I. So now that I've got those two equations, I want to reduce them to one equation in just one of those variables. So I'm going to do that using the S operator. So this is really just like any Cramer's rule problem, but we have to like rewrite these two equations using the S operator. So let me do this one first. This one is going to be I plus CSV equals 4. CSV, I hope you understand that, because the S operator is basically like a derivative. So this is like just taking the first derivative of V with respect to t. This one is 6I plus LSI, right, minus V equals 0. Okay, so this equation now has become this equation by just applying the S operator. This equation has become this equation. Okay, so I'm going to erase the two that they came from because it's now redundant. All right, and then, okay, I'm going to just I'm almost there. What I'm looking for is to set up Cramer's rule, where you take the unknowns and you kind of make a column out of them. I'm not quite there yet. So I'm going to rewrite it here. So I have I, and just to explicitly show the coefficient, 1I plus CS times V, so I and V are the unknowns, equals 4. On this side, I'm going to combine the 6 plus LS, because I want the I kind of by itself, plus minus 1 V equals 0. Okay, so now you can see it more explicitly that my unknowns are in a column. Okay, so I just replaced this with this equation with this. And now I'm ready to solve for one of the unknowns using Cramer's rule. So I could solve for I, but that's not what I'm looking for. I'm asked for V, so why would I solve for I? I'm going to go ahead and solve for V. Well, here's what Cramer's rule says. The unknown, if you set it up with, your unknowns in columns like that, with, one equation stacked on top of each other, then you can choose any one of the unknowns to solve for. In this case, I'm solving for V, and it's the ratio of two determinants. The determinant in the denominator is simply the coefficients of your unknowns. So 1, 6 plus LS, CS, minus 1. So there's the denominator in the determinant in the denominator. The determinant in the numerator is going to look almost the same, but we're going to replace the coefficients of the unknown that I'm looking for with the constant terms. So the coefficients of V, instead of CS and minus 1, 4 and 0. And then you leave the other one the same. So 1 and 6 plus LS. All right. There's my second order differential equation. Now, it doesn't look like a second order differential equation, but it is. So we just have to do a little bit of work evaluating these determinants, and then you'll see the second order differential equation. So let's do that. This determinant is 1 times 0 minus 6 plus LS times 4. So that's the determinant in the numerator. This one is 1 times minus 1 minus, right? Because you all know how to evaluate 2 by 2 determinants. Okay? And because I've got so many negative signs, I could just multiply both numerator and denominator by minus 1, right? And that'll get rid of all these negative signs. And then I've got 6 times 4 is 24, and then times 4LS over, and just, what I got? I've got 1 plus 6CS plus LCS squared. And by the way, when you start like doing this math, it's best if you put the S's at the end. Because, the L and the C and the R, those are all just constants. The S is an operator, and it operates on something. So when we transform back from the S operator to derivatives, you'll see how that works. And I'm almost there. The last thing I want to do now is I basically have this equation here. V is equal to this thing. I want to bring this to the other side. So and I'm going to change the order here. LCS squared plus 6CS plus 1 times V equals 24 plus 4LS. Okay, we're ready to, so here's my differential equation. And again, you don't see it quite yet as a differential equation. We're almost there. If I distribute the V, okay, so I'm just going to put it here and here and here. So I just distributed the V. What is this? This is LC S squared V. Well, S squared V, that's the second derivative of V with respect to T. So I'm going to rewrite this equation, transforming back from the S operator. I'm going to put it right here. So we've got LC, the second derivative of V with respect to T, plus 6C, and then SV, that's the first derivative of V with respect to T, plus V, just by itself, is equal to 24 plus 4LS. Think of S as being multiplied by 1, so you're taking the derivative of 1. What's the derivative of 1 with respect to T? 0. So that term actually drops out. You've just left with 24. Okay, and then let's just finish this off by putting the actual values of this problem. Actually, let's make this coefficient 1. Let's divide everything by LC. And if we do that and then substitute in the numbers, this is the differential equation that we have. Is it time to cut off? Okay, let's cut off here, and I'll put up the differential equation in the break so that you don't have to watch me do it.